it's positional. Let's just write that here also. So in our project, we insert each successive line in at the end of our list. Okay, we could remove from any position and insert. Of course, we will be inserting at any position. We can remove from any position. Okay, does anyone remember where we use get entry? I'm going to put these all in lowercase. Right, Gary. Thank you. That's right. When we did our display lines, we used get entry to get the value from the node and then print it out. From each node. Any questions on that? So we use that in display lines. And we'll see that we're going to be using replace. We're going to talk about that today. So replace, we can replace any line in the list. Okay, it's again positional. So we give the value and we give the value we want to replace it with and the position in our list. So far, we've really only used insert and get entry. Yes, I thank you. It overwrites it. So you specify which node you want to replace, and you give the value. In our case, it's going to be a string that you want to replace it with. Okay. So we already finished phase one. In phase one of our project, we specified the end user specified a text file, and then we read it in and put every line into the list, right? That's what we did. And then we displayed the file. And then what was the user able to do in phase one? Right? They could look at it, look at their file, and do what? Quit, right? Quit and what else? So in phase one, we could quit. And to do that, remember, we had to do :Q. And what was the other choice? Right. That's right. So for that, we did :W. Okay, so it's not much yet. In phase two, we're going to add on deleting. Specifically, the lowercase x is going to allow us to delete a single character. And DD, two Ds, will be to delete the current line. Okay. And the last thing that we're going to do is we're going to color code keywords, color code any C++ keywords that are in the file. So for example, what are some keywords in C++? Anybody? Right. Well, string is not, by the way. String is not a keyword in C++. Remember, you need to do a pound include string. Right. So, but int is an example, and for, while, right, different data types, if, class, right? So all of those, and what color should we choose? Purple or blue, right? We're going to color code them blue, but you could choose another color if you like. Okay, so we're going to color code them. How do we know if a particular word in our file is a keyword or not? Right, not always. It could be anywhere, right? It's true that a lot of lines start with it, but so how could we determine if a value is right? So here's an example. If we have a 4, right? 4 is a keyword, right? We could ask the user if they intended it as a keyword. It'd be a lot of trouble. Right. Right. So Laura, we're going to have to think about that. Right now, the default will be that it color codes all keywords, and maybe I'll give it as extra credit to only color code it if the user wants it to be, if they specify a keyword file. Okay, so we're going to have how are we going to, we look at this line, right? For int I equals 1. And we want to color code the for and the int to be blue. What are we going to need for that? Yeah, right. But what are we going to need in order to determine if something is a keyword or not? Right? There are, let's say there are 30 keywords. Anybody? So let's say we read in the word for. Right, we need to have some type of lookup, right? We're going to need some type of lookup to see whether it's a keyword or not. Right, right. So Unasia says we could create a text file with keywords. Okay, now it's going to be originally in a text file. Okay, and then we have to have it in our program to access. So we could read it in to what? Where should we put it inside our program? I'm going to put up a little poll for this, okay? Let's see what people think. Be multiple choice. Okay, where should we store the keywords?
Oh, I just noticed something, Professor. So in phase one, it says we used write, like W for write. I believe we didn't write in the last phase.
Okay, yeah, we didn't actually write. Okay.
So it would be because I was working on that this weekend, and I was like, I could use going over it in class.
Sure. Okay, so let's do this poll. Where should we store the keywords? A list, a bag. Remember we had the bag object, the bag class, an array, other, I don't know. Okay, the answers are spread out all over the place. We can't really assume anything about the implementation. We just know that we have certain methods that we could use. Same thing with a list. Remember, we saw that a list could be an array and a list could be nodes. Okay, let's see. Okay, a lot of people didn't answer. Okay, so that's it for the poll. It's spread out all over the place. The two winners equally were list and array. So somebody who chose array or somebody who chose list, how do you justify your answer? Why would you say that it's a list? Why is it a good choice to make it a list? Okay, so if we had a list of the keywords, right? So Unasia, I think, said that we're going to have, was it Unasia who said we have an external file of keywords? Yeah, so Unasia said we have an external file. We said we're going to read it in. Someone who chose list, why is list a good choice for your keywords? What method would you use to see whether it's in the list or not? somebody who used bag, you know, why would bag be a good choice? Okay. Okay, so Laura has a reason. Okay. She said we can use a bag to search for any keyword. One of the methods of bag is contains, right? You could check to see whether it's in the bag or not, right? Whereas the list doesn't have a contains, right? So, but Laura, could we order the keywords?
We could organize them alphabetically, but that might not be particularly useful. Or maybe it is.
Why wouldn't it be useful?
Actually, it would be useful because when you're searching your string to see if you're looking at a node to see if a keyword is in there, you're going to start letter by letter because it's a C string.
Okay, so we don't have to do it letter by letter. We could process it word by word. Right? We're going to process it word by word. We're going to gather up the word. Once we have a word, we're going to look in our container to see whether that word is a keyword or not. So we have to examine every word, and if it's a keyword, we're going to display it, let's say, in blue. And if it's not a keyword, then we don't. Okay, so Laura, thank you for, backing up your choice and justifying it. I see why you did it. So an advantage of a bag is that you could call contains. But if we go back to the bag and we look at how does it determine whether it's in the bag or not, how many items do we have to look at in the bag? Let's say
we look through the whole bag.
Not in the bag.
Or we look through
so let's say we have that line for int I equals 1, and let's say it's going to be, let's just write a little bit more of the code. I less than num items I plus plus. So let's say we're up to the value, we're looking up num items, and we're looking in our bag to see whether it's a keyword or not. How many values in our bag would we have to examine? Right, we're going to call it on num items, and then the algorithm for contains, let's say it happens to be in an array. How did we determine if it's in the array or not? Or if it's in nodes, it's really the same idea. How do we determine whether it's in the bag? Anybody? Do you remember that? Way back, right? So to determine whether it's in the bag or not, we looked at every single node, right? The algorithm looks at every single node, starting at the first one, and then checking to see whether the value in the node, let's say, is the same as the value in the parameter that we're sending it, the target that we're looking for. So if it's not in the bag, we'd have to look at every single value. Do you see that? Okay. Let's say that our bag, remember we did a bag of area codes. If we look for an area code like 777, let's say, not an area code, we'd have to look at every single value in the bag to determine that it's not there. Any questions on that? So even though a bag has the method, right, I see why Laura picked it, it's not very efficient. And this discussion that we're having now about what is the best way to organize our data in order to search for something is a very good segue into our topic of algorithm efficiency. So we'd like to be able to look for the values efficiently. Now, Laura said that the keywords are not in order. So first of all, that depends upon the file that we read in from, right? But let's say we're reading in from a file where the keywords are not in order. What could we do to put them in order? How do we organize data so that it's in order? Right, bubble sort. Thank you, Aya. We'll use some type of sort. So even though they might not be in order, we could always sort them. And how many times would we have to sort them in our editor? We have this file of keywords that we're going to read in to some type of container. And then Aya said we would sort it. So my question was, how many times do we have to sort it in our editor? One time. Thank you, Neza. Just one time. So in terms of efficiency, if we make our search more efficient, then it's not a bad idea to sort it once. Okay? So we could use the bubble sort or some other sort to sort it. So that's assuming that our values, our keywords, are sitting in what type of container? Okay, we're going to read them in, and we're going to store them in what? Store them in, remember we had list, bag, array. I could have added stack, right? Or I don't know. So which one? We said that the bag is not so efficient because we'd have to look at every value. Okay, so let me just say we're going to store them in an array. Okay, and then we're going to sort them if they're not sorted. Okay, and then going back to our area codes, do you remember which search? How could we search efficiently if the array is sorted? Yes, thank you. So we're going to use our binary search to search our array of keywords. Very good. Okay. Now it turns out that our keywords, this is really just to, it turns out there aren't that many keywords for this to make a big difference. We're doing it because just to learn about efficient ways to search. And it's going to be more efficient in general to search using the binary search if the values are sorted. So we're doing it more to learn about different algorithms than because for our exact example, it's not going to make a big difference if there are only about 50 keywords. So I hope everyone understands that. Okay, so now we're going to use the binary search. Yes, Laura.
Today, will we be discussing how the user can navigate through their cursor through the program with arrow keys and all of that?
Very good question. I'm putting that off for a while. So,
okay. How would they be able to delete a single character from?
That's a very, very, very good question, right?
Yeah.
I wanted to make the point. I'm doing it a little bit out of order, but I'm doing it intentionally.
Okay. Okay,
So,
sounds good.
Okay, but it's an excellent question. So Laura, if the end user opens up the file and they delete a character, what's the character that they're able to delete?
Currently, only the very last character.
The very first.
Or the very first, right? Thank you.
Right. And which line could they delete?
The very first line.
Only the first line. Okay?
Gotcha.
We're going to add in the navigation later. Okay? So.
Sorry, I know that was off topic. I know you were talking about the search.
Right. That is true. We're going to use we're going to sort them, put them in an array, sort them, and we're going to use the binary search. Okay? The reason I'm discussing this now is I want to segue to algorithm efficiency. And this is relevant when we're talking about sorting and searching. Sorting and searching are two of very common algorithms that we need in computing. We're always searching for things, and very often it's more efficient if they're in sorted order. Okay? So for algorithm efficiency, we're going to look at algorithms that search and sort. These are two classes of algorithms that we're going to examine. When you take a full course in algorithms, you'll go through many, many different types of algorithms. But in this course, we introduce algorithm efficiency, and we do it using sorting and searching. So let's say we have our array of, remember we had our array of area codes, and then we had the end user search for a particular area code. We saw that when it was in the bag, it was not so efficient because it had to just sort of look through every value in the bag to see whether it's there or not. But then we did it again. We sorted the area codes. I think they came in sorted order anyway, right? They were in sorted order. And we did a search, right? So we did it two ways. In our array of area codes, we did it as a bag, but when it was in our list of area codes, we had a bag, but then we did it in an array. And then, as Venezia said, we used the binary search. Okay, and that was very efficient. So let's say there were around 500 area codes. Okay. Now, assuming that they're not sorted, assuming not sorted. Okay, how many values in our array would we have to look at to determine whether an area code is in the list or not in the array or not in the array? Right, there are about 500 area codes. We might have to look at all the values. Okay, Laura says anywhere between 1 and 500, right? Because it could be anywhere in the array. Okay, so Unasia might have been referring to, let's say we were looking for 777. So if we're looking for 777 and it's not in the array, we'd have to look at all 500. And if there were 1,000 values in our array, we'd have to examine all 1,000. Now, Laura's right that if it is in the array, so let's say we're looking for I think 301 is an area code.
630 is in there too.
What's that?
630, I know for sure is in there.
Okay. Let's say we're looking at 301. It might be like Maryland or something. I'm not sure. Let's say we're looking for 301. Then, and they're not sorted, right? See, we're assuming they're not sorted. So it could be anywhere in there. It could be at the beginning. It could be in the middle. It could be at the end, right? So we might have to go between 1 and 500. So if we're looking for 301, even though we're not going to examine all of them, it would be, if we had to say how many, it could be between 1 and 100, 1 and 500. We're going to say that's on the order of n. N, which in our case is 500. Right? It's going to be between 1 and 500. Okay, so if we're looking for in an array for something, we might have to look at all of them. But we're not going to have to look at more than 500, right? So it's on the order of n. That's the expression that we use, on the order of n. Now, what if it is sorted? Right? We're looking at searching now. Let's say that the array is sorted. And we're looking for 777, which is not in the array. Okay? And let's say that we're not using the binary search. But the array is sorted. We're looking for a value that's not in the array. How far would we have to look?
Assuming we know the beginning and end, or assuming we don't know what is the
We
beginning
know the
and
size
end?
of the array.
Do we know that, say, the last element is 776 or something beneath it?
No.
Okay, then we would search through all of it.
Last one is.
Then, like Aya said, we would search through all of it.
Well, let me pick a a smaller value because I think that's confusing people. Let's say if we looked at 501, okay? And here, 555, let's say, something that's not a, okay? Assuming not sorted, we're looking for something that's not in the array. Since I'm just picking something that's a little bit smaller, okay? And let's say the biggest area codes are like in the 900s, I think, 939. Isn't 929 a New York one? Okay, so there are ones in the 900s. So if we're looking for 555, but the array is sorted, we wouldn't have to look through all of them. Right, Aya? And Laura and everyone else? We're assuming that they're evenly distributed, but we'd have to look up to that point, right? As soon as we got to something like 556, we would know that it's not in the array. So if it's sorted, we wouldn't have to look through the entire array. So it's already more efficient. Okay, now Uneza, it's an interesting thing you said about more than half, right? Let's say we're looking for 301, right? 301 is in the array. How would we know whether it's there or not? How far would we have to go? How would we know that we went too far, right? We're looking for 30, if we're looking for, looking for 555, we're saying we would look up to less than or equal to 555. As soon as it was greater than it, we would know if it's not there. Okay, same idea for looking for 301, right? Which is in the array. We would look up to less than or equal to 302, 301, right? Less than or equal to 301, okay? So if it's sorted already, it's more efficient. We don't have to look at all of them if it's not there. And in general, there or not there, sometimes it would be in the beginning, like if we were looking for 201. Sometimes it would be at the end if we were looking at 929. But sometimes it would be in the middle if we're looking, let's say, for 501. Now, going back to what Unasia said before, on average, we would have to examine half of the array. Sometimes it's in the beginning, sometimes it's at the end, sometimes it's at the middle. On average, if we do this hundreds and hundreds of times, on average, we'd have to look at half of the array if the array is sorted. So that would be n over 2. On average, we look at n over 2. I wrote what is, I want what if. Okay. Let's see, we're going to do a third case now. What if the array is sorted and we are using the binary search? Okay, so let's review that, what we did a while ago. Okay, using the binary search is going to be even more efficient than just having it sorted and doing a linear search. So for this one, not using the binary search, we're going to use a linear search. Okay, and this one also. Okay, but now we're using the binary search. The array is sorted, and we're doing searching, right? We're doing searching, algorithm efficiency for searching. But now we're using the binary search. Okay, and there are about 500 area codes. Let's go over the algorithm for the binary search. Where do we look first? What item do we look at first in our array? Middle. Thank you. We look at the middle element, right? And then we see whether our value is greater than the middle element or less than it. Remember, I demoed with a dictionary where we looked at the middle element. And then once we determined which half of our array the area code is in, we don't have to look at the other side of the array at all. So that was the efficiency, that each time we divided the dictionary or our array in half, and that makes it very, very efficient, only because the array is sorted already. Okay, so let's say it was less than the middle element. Then instead of looking at 500 elements, we'd be looking at less than 250 elements. And then let's say we divided it in half again. Instead of looking at 250 elements, we'd look at less than 125 elements, and so on, each time dividing in two. Okay? So how many in general is it going to be to search a sorted array using the binary search? Anyone remember? Each time dividing by 2. Okay, so whether it's there or not there, anyone remember? We keep dividing by 2. So because 500 is not a power of 2, I'm going to say it's 512 instead, okay, which is close to 500. Okay, so if we start off at 512 and we divide by 2, okay, so Laura, it's something like that, but it's the opposite, right? Half of 256, half of 512 is 256. What's half of 256? Each time we're dividing in half. What's half of 256? 128. Thanks. Right? Half of 128? 64. Then comes 32. Then comes 16. Right? If we keep, let's say it's not there, we keep searching smaller, smaller, smaller. 8, 4, 2, and 1. How many searches is this altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 2 to the 9, right? That's where Laura got the 2 to the 9. It's 2 to the 9 is 512, but if we want to get the value 9 out of it, then what do we do? The opposite of 2 to the 9 is, what's the operation that's the inverse of 2 to an exponent? What's the inverse of 2 to the n? Okay, that's one guess. That would be the opposite of n squared. So if we take the square root of n squared, then we get back n, right? But we're doing log, right? So log let's see. Log base 2 of n. And in our example, it's log, really lowercase, log base 2. Just want to make that a lowercase. Of 5112. Put that in regular. Is equal to 9. Okay. So we see that it's quite dramatic, right?
Do we just refer to 9 as the number of searches required, or?
Yes, that's the number, and that's the max, because we could find it before. Okay. Now, if we were to double that, if the number of values that we're searching, if n were equal to 1024, then what is log base 2 of 1024? 10, right? Then it would be 10 searches max, right? And if it was 2048, then it would be 11. So the number of searches only goes up by 1, even though we're doubling the number of values that we're searching. Whereas if we did a linear search, if we had 500, right, we would have to search, and it wasn't there, we'd have to search all 500. If we doubled it, we'd have to search 1,000. If we doubled that, we'd have to search 2,000, and so on. So it goes up, it's always going to be on the order of n. And the beauty of the binary search is each time we double it, it goes up by log base 2 of n, right? It goes up by log base 2 of n. It only goes up by one search. N equals 9, then n equals 10, then n equals 11, right? So it's much, much, much more efficient. We only see the efficiency really kick in when we have large, large values. If we only have 10 values that we're searching through, then you might as well do a linear search. Okay, Laura, you could answer that, right? When we did the area codes, it didn't matter that they were integers, right? They could have been names because we're looking at the index into the array. The index into the array is the important thing, right? When we look at the middle element, we're looking at the index into the array. Right? Laura, does that make sense?
Yeah, it does. I was getting confused because searching for 512, thinking 512 was the area code, but now I'm remembering that it's just the index.
Right. We're searching for we weren't searching for 512. We were searching 512 values. Okay, we were searching for the area code 555 in a list of 512 values. Or we were looking for 301 in a list of 512 area codes. So 512 refers to n. Okay, so when we refer to n, that's the number of values that we're searching. Okay, so taking a step back again, remember that we're talking about searching, and we're talking about doing an efficient search. How could we efficiently search through values? Okay, so a linear search would mean that we'd have to look through all n. If they're sorted, then it would be n over 2. But if they're sorted and we don't do a linear search, instead we do a binary search, then the search is going to be log base 2 of n. We sometimes abbreviate that by just saying log n, and we assume that the base is 2. Okay, so different searches. Linear search, n. Binary search is log n. Okay. So binary search is much more efficient.
And linear search, when sorted, is n over 2.
Right. Now, even if it's n over 2, we still call that n. Okay? And the notation that we're going to use is O of n or O of n log n. And O stands for order of. And you could think of it as being approximately. It's on the order of. So if I tell you that someone makes on the order of 6 figures, right? It's rude to ask someone their salary, right? It's not socially accepted to say to someone, how much money do you make? But we do say about people, we say they make 6 figures. What does it mean if you say someone makes 6 figures? Right. 100,000 range income. Now notice what Peter wrote, right? It really could be 999,999, which is a lot more than 100,000. But we say on the order of 6 figures, on the order of 100,000. So if you say someone makes 6 figures, we see that that's an approximation. It's just giving us an idea. They're not a billionaire, but they're still making a nice salary, 6 figures, right? So that's the idea behind algorithms. When we talk about algorithms, it's the number of steps in order to accomplish our goal. And it's going to be tied to the size of the file, the size of the array, the size of what we're dealing with, the number of area codes, the number of keywords. Okay, so if we have to search all of them, if there are 1,000 of them, then n is equal to 1,000. If there are 1,000,000 of them, then n is equal to 1,000,000. If we say it's O of n, it doesn't matter what n is equal to. It means that we have to look at all of them once. That would be an algorithm that's O of n. Right? But if we could get it to O of log n for searching, that would mean instead of searching 1,000 items, we're going to search just 10 items, right? So that's much, much better. And we said that if it's, right, 1024, twice of that is 2048, twice that is 4096. So if you have about 5,000 items and it's O of n, that means you're going to have to look at 5,000 items to determine, to search if it's in your array, not in your array. But if it's sorted and you could use the binary search, right? 4096, if it was 4096, that would be only 12 searches. So we see that if something's log n, then it's much better than n. It's much smaller. Any questions on that? Okay. How many students are there, undergraduates at the College of Staten Island? On the order of? Anyone know? Not exactly, but on the order of. Anyone know? I mean, I don't know exactly, but I think it's on the order of 10,000. Right. So Christopher says 13,000-ish. So I'm saying it's on the order of 10,000. If I say there are 10,000 and you find out that there really are 13,000, then that's on the order of. It's around that, right? Now in algorithms, this is very significant, the order of an algorithm. We talked about searching, but let's just for a moment talk about sorting. I mentioned the bubble sort. I remember asking you how many of you covered the bubble sort, and not everybody had. But let's say, Aya, did you study the bubble sort?
No, I haven't, but I've seen like videos of it, so I'm not too familiar.
Okay, so the bubble sort, instead of having a single for loop that goes through the list once, it turns out you can't sort the values in an array by just looking at each one once. That would be O of n. It's got to be more than that, right? You can't get them in order by just looking at them once. For example, let's say we were in person. Okay, imagine that we're in person. And I ask Aya to put the class in sorted order by height, right? Using the bubble sort, we'd have a nested loop to do that. And we would have to look through every student, and then for every student, we'd have to put them in their correct position using the bubble sort. Okay, so it turns out that we're using a nested loop. We're going to look at the bubble sort in more detail, but now we're just talking about it. Yes, so Inasia, that's exactly right. We have a nested loop, and it's going to be on the order of n squared. So it's an expensive sort. Okay, so the bubble sort is an expensive sort. In this course, we're going to be looking at all sorts of sorts, many different sorts, and some will be more efficient than others. Okay, let's look at other algorithms that we've discussed besides sorting and searching. Let's talk about our stack for a moment. The push operation. Let's say we have n items. On our stack, and we push. I'm going to take this off from here and just put here. If we push, what's it going to be? O of what? To push an item onto our stack. Okay, think about it. Where do we push onto our stack? And it doesn't matter if it's an array or it's a linked list, if it's linked nodes. Let's imagine that it's linked nodes for a minute. Where do we add onto our stack? At the top, right? Top of the stack. So if there are 3 items on our stack, 100 items on our stack, 1,000, 1,000,000, how many operations do we have to do to push onto our stack? O of what? Thank you. It's O of 1. We only do one operation, right? We hook it onto the beginning of the stack. And if it's an array, remember we put it in items subtop, right? We add one to top and we put it in items subtop. That's a direct access. Again, it's O of 1. Okay? So this doesn't work for searching, and it certainly doesn't work for sorting, but we could say, what's the order of the push for a stack? O of 1. Okay, what about the pop? O of 1, right. You see, you're getting the idea. Sometimes it's only one operation, O of 1. So that's what makes a stack so efficient. But of course, we don't search through a stack and we don't sort a stack. So it depends upon the algorithm. So the algorithm for push and pop are very efficient for a stack. Okay, if we implement it using an array or linked nodes. Okay, so we're talking about on the order of and different efficiencies for different algorithms. What is the efficiency of different algorithms? So for searching, we said that the linear search, if there are 10 items or 500 items or 1,000 items or 1,000,000 items, we have to look at on the order of n of them. But the binary search is going to be log base 2 of n, much, much more efficient. Okay, so the types of O, order of, O of 1, we saw for stack, right? O of n, linear search. O of n log n, binary search. Any questions about this in general?
The additional n in front of the log n, is that just a notation feature, or is that implying something about n being yet again multiplied to the log n?
Yeah, I'm sorry, I typed it wrong.
Oh, okay, it's just log n.
Right. You see over here, I wrote
Yeah.
log n. Thank you for noticing. That's a typo. It's O of log n. It's just a typo. O of n and O of log n. Now we're going to see other ones that are O of n log n. Okay, but not under searches. Thank you for catching that. I didn't mean to put that there. These, if we look at for the stack, we have O of 1 for push, O of 1 for pop. Okay, let's talk about a little bit more before we take a break, right? Let's talk about get entry for our list. Okay, think about get entry for a moment. Get entry, we give it a value, right? And then we give it a position, right? We want to get the entry at a particular, if you look at the array-based implementation first, right? We look at the array-based entry, we give it a position, and we want to get back the value at that position. Okay. Now let's say that the values are sitting in an array. Okay, so now we're looking at list. And the algorithm that we're considering is get entry. Okay, and we're going to send it a position. And let's say for our list, it's implemented using an array. What's it going to be to get the value at that array position? Right. Okay, did anyone answer this for this one? Did the, Gary, what do you think it is? O of what? Array implementation, and we're doing get entry. We give it a position, and we want to get back the value at that position. It's O of what? Right, I think Laura just wrote it, right? O of 1. Okay, because we know that arrays have direct access, and we're making use of it in this get entry. Okay, now let's remember the linked nodes implementation. Okay, if it's linked nodes, okay, so the array implementation comes first in chapter 9. But if we look at the linked node, this happens to be on page 275, how do we find that value that's in the particular node that's specified in the parameter? We cannot index into linked nodes. Doesn't matter if it's sorted or not. In our list, it doesn't matter. Remember, we're not doing any type of efficient searching. So if you remember, we call get node at. And remember, get node at has to traverse through the list to get to that particular node and return its value. So what is it? O of what? It's O of n, exactly. So we see that get entry is not always the same. Depending upon the implementation, it could be very efficient, O of 1, or it could be very inefficient if it's linked nodes. So these are we have to consider this when we choose an implementation. We have to consider whether to use the array or the linked, and it's a trade-off depending upon the types of operations that we're going to be doing on that list. Okay, so it's not always the same, even for a particular method. It depends upon the implementation. Okay, so the types of orders that we've seen so far, O of 1, O of n, O of log n, right? And we'll see a few others. We mentioned O of n squared. We'll see that that's because there's a nested loop and we go through the array more than one time. We don't just go through it looking at every value once. And it turns out if we're sorting, it'd be very hard to sort an array and just look at each value once. When we're sorting, we have to compare values to each other. So we have to go through it more than once. So we're going to be talking about that as well. Any questions about this? And this is all discussed in chapter 10. We'll keep coming back to algorithm efficiency. This was an overview, and I wanted to tie it to problems that we've already seen, like searching for an area code. And what we're going to be doing in our project, which is searching for keywords. Okay, so we're looking at the more efficient ways, but always keep in mind that if it's a small file, then it doesn't really matter. Okay, you could have it, you know, keeping it in an array is an efficient way of storing them because we're not inserting or deleting any of the keywords. The keyword file stays static. But we're using the binary search just to make the point that we're using a more efficient sort, a more efficient search. Any questions? Okay, so we're going to take a break. When we come back, we're going to continue our discussion on linked lists. We'll talk a little bit more about algorithm efficiency, but we'll talk a lot more about phase 2 of the editor when we get back. Okay, so we'll come back at 11. Whoops, let me put it in the chat. 11:50. Okay, so see you then. Okay. We're back. Let's talk a little bit more about the project, okay? Um, let's first talk about deleting. We said that X deletes the current character, and as Laura pointed out, that's just going to be the very first character, the first time the user deletes, and then the next character, the next character. If they type DD, it's going to be the first line. Okay? Laura and everybody, we're going to be talking about changing the position of the user a little bit later. Okay. But now, what's involved? Let's start with DD. It's always going to be the first for now. Okay, what's the algorithm for deleting a line? Okay, so the user types in DD, and we're going to have to discuss how they could type two things if we're only reading in a single character. But let's hold that for a moment. What's going to be the algorithm for deleting a line? Okay, so the end user types in DD. What does our code do? Anybody? Which method? Oh, thank you, Janway. That was my question. That was exactly my question. Which method of list are we going to call? And Janway says remove, thumbs up. That's it. We're going to be calling remove. Yes, Laura.
Does this portion depend on us having the right to file method implemented since we haven't done that yet? Okay.
Okay, so Gayatri can't hear, but the others can hear me, right? Because you're answering me. So, okay, thank you, Laura. Okay, great. Terrific. Okay, so we're talking about phase 2 and deleting, and Janway wrote we're going to call the remove method. Okay, so we're going to say that the current line is going to be 1, right? The current line is 1. It's not always going to be 1. That's going to change. But for now, just note that the current line is set to 1. Okay, so you have the current line that the user's on, and that's going to be set to 1. Remember, we count from 1. And if they hit DD, don't hard code 1 in there. Just put in the current line. They're going to delete the current line. And that means calling the remove with whatever the current line is. So we're going to invoke the remove method of our list.
Oh, baby, baby, we belong.
Okay. Are there any questions on that? Okay, so that's the idea. We're going to, now let's just discuss for a moment. We have DD. Okay. What else? What if they type X? Right? You want to delete the current character. Delete the current character. So we're going to have remember that the lines are counted from 1 and the positions going across. And as we have what's on the screen that the user sees, and we also have the position going across. So, Laura, you have a question?
So I noticed that DD is 2 characters, and the way we've got it set up now with get character, that only reads in 1 character at a time.
Right. So
What
about
kind
a
of
minute
adjustments will we
ago,
need to?
I mentioned that.
Oh,
I
I'm
said we're
sorry.
going to get to that. Okay?
For some reason, it didn't make it to my ears. I'm sorry.
That's okay. It's probably didn't make it to many people's ears then. Okay? I just want to, you have to be consistent about what you call 0 and what you call 1. So I want to emphasize, I want to leave this at 0. It's a little bit confusing, but the lines in our list are numbered from 1. The position in the upper left-hand corner of the screen that the user is looking at is 0, 0. Okay? You have to be consistent in your code about that. Okay, so the current line, let me just be specific here. In the list is set to 1. The current position of X on the screen is 0. Okay. So let's just talk about the algorithm for a moment for X, and then we'll come back to that second D that Laura just asked about. What's the algorithm for deleting the current character and making sure that the user can then see that it's gone? What are we going to be changing? We replace the node with a node that doesn't include the deleted character. Okay, good. We're actually going to replace the node. Now the node itself has a string. So first of all, we have to get that string. Okay? We could use get entry to do that. We get the string. And then we have to remove whatever character the current character is. And we're going to use a string method to do that. There is a string method. I remember string is a class. There's a string method called erase. Did someone raise their hand? It was behind my, or did someone have a question? No, okay, something popped up, okay. So there's a string method called erase, and that's what we'll use to, you don't have to, but that's the easiest way. Now erase the current character. Don't always do one because later on it'll be different, okay? And then, so we want to erase and replace. We're going to erase, and then as Laura said, we're going to do a replace. Okay. Any questions on those two? Okay, so let's go back to DD. DD, we're going to, yes, Elizabeth.
So in order to immediately display that change to them, what I imagine we'll need to do is clear the console like of what we're looking at and then redisplay all of the lines. But I'm not familiar with how we clear that console.
Oh, clearing the screen. We mentioned that, but let's just put that someplace up here to clear. Anyone remember? Clearing the screen, and this is specific to Windows. How do we clear the screen? Oh, thank you. So Inezia put it there, but I think you need to have quotes around it, right? So it's system and then clear screen, and it has to have quotes around it. So okay. Okay, so then, and Laura's right, we want to clear what they're looking at, which is the old version, and after our change, and then we do our display lines again, and they see it the new way, the updated way. Now, I'm recommending that you use a, instead of if else, if the command that they're typing in is an X, do this, else if the command is a D, do this. What do we use instead of a bunch of if else's? Cases, but that's cases are part of what type of statement? Right? We have individual cases, switch, exactly. So we're going to have the switch statement, and then we'll have different cases. So let's say it's an X, then we're going to do whatever X is. If it's a colon, then we're going to look at whether the next character is a W or Q. So it's similar to that idea. If they read a single D, then we go to that case, and then we go ahead and we read the next character, okay, whatever the next character is. And if the next character, right, so we go to that case, and then we do another get CH. We do another get CH, and if it is another D, then we go ahead and delete. Okay, otherwise we just ignore it. So if they say DX or DT, we're going to ignore that second one. Okay, any questions on that? If they DD, they're going to delete it. So does anyone in the class have are they right now working on a Mac? Anyone working on a Mac where they could bring up a terminal? Yeah. if someone types in DD, we want to delete the current line, whatever the current line is. So if they do a single D, then we'll go to, in our switch statement, one of the cases will be a single D. We go to that case, we do another get ch, we read in the next character. And if it's another D, then we delete the line. If it's some other character, we do nothing. We don't go ahead, we don't delete it, we ignore it. Okay. So, okay, great. Okay, so I'm going to share my terminal window. Okay. Okay, and let me go ahead and share that. Okay, hold on one second. I don't know why it's not showing up. Hold on one second. Let me try that one more time. Okay, now I see it. Okay, so this is one of the files we were using last time. The quick brown fox jumped over, and the lazy dogs is on the next line. So now, you see the cursor is in position 0, 0, and I'm going to type the letter X, and the T gets deleted, and so on. So you can only delete from the beginning. Laura?
Are you not doing :X?
No. X
Okay, so we
itself.
should have two separate kind of like switch statements here, or at least two different groups here. One is where the first character is a colon, and the next is where it's either D, like DD or X.
One switch statement. One switch statement, and if it's a colon, you go to the colon. If it's an X, you go to the case X. One switch statement.
So if it's colon, I should go like colon, and then there would be if statements after that for W or Q.
Right.
But oh, okay. I had mine arranged differently. Okay, thank you.
Okay, makes sense. So we want to, okay, let's say, now I can only delete the first line. So now I'm typing 2 Ds. You can't see that, but there's 1 D, there's a second D. Okay, so we can only delete the first line, 1 D, second line. Now it says no lines in the buffer at all. Now we're not doing any undos, so that's it. You can't, at this point, we could do colon and Q in our scenario right now, but we're going to, remember we had to do colon Q exclamation point. And now if I go back to that, everything's still there because all those deletes didn't take place. I didn't write anything out. In phase 2, we're going to add in the writing. So let's say I do X, 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 okay, colon, W, and here I'm going to say quick updated, okay, and now I'm going to do colon Q to quit. Colon Q exclamation point. Okay, and now quick updated. Okay, and there it is without the word the that I deleted. It starts off with quick because I wrote it out. Okay, any questions on this? So we're implementing X, DD. So that's going to actually change the list, which we didn't do before. And then we could write it out and give it a new file name. Or if you don't give it a new file name, it'll just write up that one. So let's do that. Let me take out the word quick, colon W, and then it changes this one, colon Q. And now the word quick is missing. Any questions on this? Okay, so I recommend that you do one little piece at a time, write it incrementally. Now each phase is an increment, but within that, try to implement just X without writing. Just see if you can do a single X and it'll show it to the user on the screen with that first character gone. Okay. Then implement DD and see if you could delete a complete line and display it to the user, right? By clearing the screen and displaying it again. So add in X, then add in DD, and then worry about the W, writing it back. Quit you already have. You have to be able to demonstrate that quitting didn't change anything. And if you write it, you could write it back to the exact same file. It will have the changes reflected in that file. Okay, so we're getting a more powerful editor now. We can delete things. We're restricted because we can only delete from the beginning. I wanted to emphasize this because I want to motivate why we need to navigate through. Right now, we're not navigating through. Okay, so everyone, when they delete, will be deleting from the beginning. Any questions? Okay, so I'm sure you'll have more questions once you start it, but because you did phase 1, you're already in better shape because you have the framework put together. Now, right now, all the commands are going to be single characters, or in the case of DD, double characters. And for the next, not in this phase, not in phase 2, but in phase 3, we're going to have a new class, a command class, but that will not be for this, this phase. So for this phase, you're just reading in whatever command the user entered, and you're going to that switch statement. Now, we already did that because you already did the colon. We're just adding to that switch statement, adding different cases. Okay, I want to talk for a moment about groups. Whenever we work in groups, very often they're going to be issues, sometimes small issues, sometimes big issues. What type of issues do we have to deal with? Well, sometimes one person is doing all the work. Sometimes one person insists on doing all the work. Sometimes people are not pulling their weight. And that's one of the reasons why we have the different roles. So we have different roles so that so everyone has a very predefined role in the group. So the convener and the tester, they take responsibility for that role on the one hand. On the other hand, everybody has to understand all pieces of the code. Okay? So sometimes another big issue that could come up in groups is that there could be poor communication. So it could say one person is there but not speaking at all. One person didn't show up. One person's not in touch at all. Okay? So that's something as a group that you have to work through as though you were in a real life situation. Now, sometimes it's above your capabilities. Sometimes it's something that you don't know how to deal with. And if an issue like that comes up, then you have to go to the project manager. And for this scenario that we're working in, I'm the project manager for each of your specific projects. So you have to let me know if there's some issue. Maybe somebody's not communicating. Maybe someone is not including everybody. There's so many things with group dynamics that can come up. And you want to try to get everyone involved and everyone doing their role. And if not, then let me know if something's going wrong. Now, let's say someone dropped the course, and so all of a sudden you don't have a full group anymore. Let me know. Sometimes somebody dropped the course. For example, today, not everybody's here, but I don't know if someone dropped the course or if they're just absent today, right? So you have to try to reach out to them and see what is their status. Now, if there's an issue, let's say you end up being the only one in a group because someone dropped the course, you have to let me know that person didn't show up, and then we might have to reshuffle it. So you might end up with another person in your group if someone is by themselves. Okay, so if I ask you to accept another person in your group, please be gracious about it and just, say sure and work with it, because that's what happens in the real world too. It's not a popularity contest. It's not like the project manager says, who would you rather work with? Sometimes a job needs to be done and they just say, this is your group for this project and you have to deal with it, right? So we are trying to model real life on the one hand. On the other hand, if there's a real issue, as there could be in the real world, you go to your project manager and you say, this person's not helping at all. This person's taking over. This person's not sharing their code. There could be so many issues, right? But this is one of the things that employers want to know is, have you worked on a team? Are you a team player? So it's an important skill to practice in our sandbox here, where we could just experiment. And when you get to the real world, first of all, your resume will be better. It will be stronger because you've done a group project. And second of all, you'll be more capable of dealing with working on a team. It's a very important skill. Okay. Of course, everyone's going to have individual concerns, issues. So I'm very willing, eager to speak to you individually to deal with that and try to make it work. Any questions before we go to the breakout groups? Does anyone have so today, it's not due today. Today you should try to implement X and DD, right? We have a little less than an hour left. Okay, so the : W instead of opening up your file initially as an IF stream, you can just define it as an F stream, and you can open it for input, right? You've probably seen this in a previous course, and you could read from it. But if you open it for when you write to it, you can just write over it. Now, what you have to be careful about with writing is that I think Laura, somebody said at one point that it's good practice after you read the file to close it. Okay? Why is that? What happens when you open a file and what happens when you close a file? Let's talk about opening a file. When you open a file, there is a file pointer. The file pointer starts off where in the file? If you have a file pointer. At the beginning, right. Starts at the very beginning. A very good place to start, right? Start at the beginning. So you're at the beginning of the file, and if you're writing out, you keep writing out, and the file pointer moves down as you write. You end up at the end of the file if you're writing to a file. When you close it, then you're ready to open it again and put the file pointer back at the beginning. Okay? So this is something you've either done or you could easily look up, opening a file, closing a file, and then you can write out to it. But even before today, just do X and DD, and then you could just see on the screen, did it update it or not? Okay. Unasia, does that answer your question with :W? Okay, great. Okay, so we'll go into groups. Try to get at least X working, try DD, and see if you clear the screen and display it again. Do you see the changes reflected? Yes. Yeah, sure. I'll share the notes. Any other questions? You share the notes right away.
I still have some more questions on W. What exactly is supposed to happen in our program when we do type W? What should we be seeing?
Okay. Well, nothing changes if the user types in a W. They don't see something different, but the current file is written out. If they do :W and write a file name, then it'll write it to a different file. Okay?
I don't know that we covered that.
Gary said, do we use OF stream? So you could open it as you could just deal with it as F stream, and then it'll be for input and output. So instead of IF stream or OF stream, just use F stream. Okay? So
we really, yeah, I don't really know. I mean, maybe somebody in the class can correct me if I'm wrong, but did we actually go over what the implementation would look like for choosing a different file for our program?
Choosing a different file.
Right, when the user, you said the write mode allows us to.
Okay, so let me stop sharing this for a second. I just want to share the editor one more time. Okay, so right now you see it says brown fox jumped over. Laura, you see that, right?
Yes.
Okay, so let's say I do DD, okay? And we delete the first line. Okay, so now it's gone. Okay, if I do :W, right? This is called quick updated. This file is called quick updated. So now, see at the bottom it says quick updated is written. now I'm going to actually quit. So I'll do a Q to get out of this. DD erases the current line, which right now is at the top. Yes, Christopher. Okay. So now if I open up Quick Update it again, that first line will be missing. So W writes the file out. Laura?
Yeah, I'm a little lost. I don't know that we did this.
When you said did this, like you should have done it in 126 or 211, writing to files. So do you mean you didn't do it in 126 or 211, writing to a file? For example, someone
never saving it or making it permanent,
right,
or
right. Gary said OF stream, so you probably saw that someplace.
I mean, we've done many projects reading from files, but we have not had any projects where we were supposed to write to and save it to a file.
Okay.
Personally.
Okay, so leave that for last. Okay, maybe we'll go over it. Okay, it's not a huge thing, because the same way that you let me just let me stop sharing this for a second and go back to our notes and share the notes. Okay, it's also something that you really could look up very easily. You know, like if you didn't do it in class someplace, then you could look it up. But I'll just tell you what to look up. Okay, and that is that if you have F stream, let's say it's called my file. So you can read into it this way, right? You could read into this way, but you could also write out to it the same way you do a C out. So you know, like when you do a C out, we're writing to standard output. But you could also write to a file that's not standard output, that has a name, and you just can write to that file the same way that you read in from a file. You could write from a file using, right, this one redirects it to the file, and this one redirects it from the file to, so you could take a variable, which is going to be the string that's in the node, and write it out instead of doing a C out. Instead of doing a C out, you could have the file name.
Right, but then how does the user then interact with that? Like I'm familiar with putting, let's say, a string that we already know as the programmer into the file.
Right. Right, so you could read into a string and you could write out from a string, the same as C in and C out, but with a file. Maybe you haven't written to a file, but it's the same as writing to C out. The only thing you have to make sure to do is to close the file and open it again so that you're at the beginning of the file. And so you're writing over what's there.
But
what does it mean from the user? The user just types a colon, right? And then you go to W.
Right.
If they do W and nothing after it, right, you're going to read in the next thing that they type. If there's nothing there, if they just do a colon and a W, then it's just going to write out to the current file. Why don't you
How do we create a variable for that that statement?
Oh, so it's going to be a string the same way that the file name, when you read in, is a string, and you open it, giving it the name of the file name. It's the same exact thing for an output file. But since people haven't done this and they seem a little confused, then for this one, for this phase, let's say we're going to just do, we'll leave the next thing for the next phase, okay? Colon W is going to write whatever the current file is that's already in Fstream. Right? Is that simpler to see? Just write the current file. All you have to remember is to open the file again. Close it like you always do. Open it so that the file pointer is at the beginning, and write it out again. Write in a loop, just write it out. Okay? So call your own method. If you don't want too much code in your switch statement, we're going to just do the same file. Laura, does that make sense? So instead of doing a C out,
So just saving it, really.
right?
Okay.
We're going to do an F stream. You'll see once you do it that you'll say, oh, that was all it was. It's just going to have a loop that goes through the list from the beginning. Remember, it starts from 1. Get entry for every node on the list. Instead of doing a C out, which will do it to standard output, you're going to use my file or whatever your Fstream variable was, and you'll use the double greater than sign to write out to that file. Okay, so I guess until now you've just been doing in file, right? So I think I just said it in reversed order, what I just said with the greater than, right? That the C out uses this one, right? Let me just make that lowercase.
Yeah, I guess I'm familiar with sending a known entry into the file using like the input and output stream operators, depending on what we're doing with it. I am not familiar with all of these different methods of retrieving input from the user as they're typing it and incorporating that into this process.
So let me go.
So if the user is like writing, I think you said that we would save it for later, but like I guess what had been confusing for me was initially trying to figure out how I would take the user's string entry as they were typing it and then save that into the file location. Because normally I might store that in a variable, but we don't know how long they're going to be typing.
They type until carriage return.
Okay.
Just a get line. Right? They type until carriage return. Okay? But let's leave we're going to do colon W by itself. It's going to write to the current file. That's already saved in Fstream. Okay? Let's see what Deanna wrote here. So my file, writes out. Just like C out. You see, Deanna, it's just like C out. But instead of writing to standard output, you're going to be writing to a file. Okay, great. Okay, let's give everyone time to work on it. And then, of course, you could ask me questions as you're working on it. And if anyone has group issues, also write to me. Let's see who's here today. Let me just do one quick look at who's here. Of course, I'm not going to be able to see right away who's absent. But once you're in groups, go to the group that you were in before. If anyone is by themselves, of course, we're not going to know if the student dropped the course or not. That's something I just don't know. Unless they officially dropped, if they just stopped coming, I won't know that. So that's a little tricky. Hopefully most of you are in groups of 4, so that won't be an issue. If anyone was in a group of 2, that will be an issue. But let's see, let's start the groups and then we'll deal with it afterwards. And if anyone has specific group issues, please let me know. Okay, so now it's 12:36. We're just going to go till 1, and then we'll regroup. So just going to start it, and we'll continue on Wednesday. Okay, so I'm going to start the groups, and I'll try to set it so that you can rearrange yourselves. Allow attendees to switch groups. Okay, and you're going to have to switch yourselves around. Okay, so see you at 1.